So, welcome everyone to this week's Origins colloquium. It's a pleasure to have Oliver Herbert visiting and assisting in the Class in Vitro program. And it's nice he's able to give us a talk as well this week. So, Oliver received his PhD. We were just trying to work it out 2022. We can still remember that far back. From the University of St Andrews, working, I think, with Peter Voigt, is that right? And then basically is now in his first postdoctoral position as an Ariel Fellowship position based at the University of Vienna, working in Manuel Goedel's group. And Oliver is an expert on exoplanets and their atmospheres, and we will hear about his work on rocky exoplanets and their diverse atmospheres. So welcome, Oliver.
Yeah, thank you very much, and thank you all for joining. The content of this talk is not just focusing on one paper or so, but rather a diverse set, therefore also quite a large group of collaborators throughout the years. Especially want to mention Rob, and who's now a postdoc in Groningen, working with Tim Lichtenberg, and Leon Sreinig, a master student of mine. And yeah, that's just the introduction for everything. And because of the diverse background of the people in the audience, from some galaxy or black holes, people not going into depth on many places, but rather an overview of many different things. If there are any discussion points, I'm here next week as well. So
we have 30 minutes for
points
today.
And 30 minutes for discussion anyways. So the massive in-depth discussions are for the discussion points in here. So let's start and go through this, if my computer allows. Yes. So what are we expecting in this talk? Why do we care about rocky planets? How can we kind of constrain their bulk composition? Then going further into how can we constrain the surface composition? What can we do with the atmospheres? What happens in the atmospheres? And are there any observables? Can we actually observe these differences or not? And that's basically the structure of the talk. So let's deep dive in. Rocky planets. People that have seen some planetary talks will have seen some sort of this plot. So planetary radius versus planetary mass. And there are plenty of planets, more than 7,000 by now, actually 2,000 in this plot, where we actually do have a mass and radius. No error bars shown because they're too large, basically. But there are lots up here in the top. Those gas giants, they are interesting. They are quite nicely observable. But for this talk, we consider everything in the bottom left corner. Those tiny ones, those actually rocky ones that have an actual surface, not too much of an atmospheric pressure, not a huge envelope of gas, but just the bottom left corner here. Those are the rocky planets that we care about this talk right now. So if we look in our solar system, just some examples. Mars, we actually do have rovers on. We have some images on those differences of the surface. There are already quite a lot of things that are super interesting there, like the layering, the sheets of the rocks. If we then go further in throughout our solar system, we actually do have images of the surface of Venus as well from the Russian missions back quite some time ago now. Probably with the current state of funding in the US, there are significantly less missions going to Venus soon, but who knows what happens in the next, 15 years or so. So maybe at some point we actually do get some more Venus missions that fly. Who knows? But yeah, we do have also surface features on Venus, also for Titan. The Huygens mission just landed there quite some years ago now. There's some ice features, there's some lakes there, there's some weather going on, really, really interesting. But for exoplanets, the best we will get for their actual surface is artists' impressions, like magma oceans. We don't really know how they look like. Do they look like this? Do they what are their surfaces? For the colder ones, we will not land on any of those rocky exoplanets. So we have to think about how we can actually get any information about the surface, about the interior, because the interior has also many differences. many different tectonical regimes that could be there. How can we kind of constrain that? And that's basically my research interest. So the first part of it is that there are just many things going on in that atmosphere. Now, a bit of a sketch of an atmosphere, there's stellar radiation going in. So we have photochemistry in the atmosphere. Cosmic rays may also change things, may help in the evolution of life at some point, who knows? There's interaction between the atmosphere and the crust, volcanic outgassing. If biology is present, biology also produces some gases, drags some nitrogen into the lithosphere, basically, or throughout the atmosphere. We have cloud formation. There's different atmospheric mixing, and also especially the atmospheric loss to space. So can the atmosphere actually exist? There's a starting atmosphere. It will be lost through time. And if we're too close to our host star, well, most likely any atmosphere will be stripped, and we are left with a bare rock. It's just nothing of an atmosphere. And then we try to look at transit spectra of those planets, and we see a flat line because there is no atmosphere. But let's assume for now that our planets have atmospheres. We can also have a discussion about atmospheric loss, but that's not the focus of this talk today. So from just looking at different compositions of our of the stars that we have, because somehow that will be linked, because the stellar composition is somehow reflected in the composition of the protoplanetary disk. In the disk, at different temperatures, we form our different planets, and not all of them are the same as the solar system. So what do we see in these plots? Lovely geologists doing triangle plots. So it's not just 2 elements, but 3. So in the left triangle here, for example, pure aluminum would be on the bottom left, sodium on the bottom right, calcium on the top. And any of these points is basically a combination of them. They always add up to 100% for these given 3 elements. And we see that for the different stars, which are the blue dots, we have a huge range already. The sun, which is this diamond here, is roughly centered, actually, interestingly. But depending on where we are, which star we are looking at, there's a large variety to be expected. Also for the planets, which have a different process or some different process in the composition. This is based on some condensation sequences, basically. Also for the iron, if one includes the iron, magnesium, and silicate, which is basically how much core there would be on a planet to how much mantle there is on a planet. There's also a large range, some different groupings in there. We go in more detail into this in a paper led by Rob, and that is currently under review. So I'm just giving some peeks there. You still have to wait a couple of months probably until it's actually published at some point. And what I actually want to focus here on is there is a huge diversity to be expected. And that diversity also comes not only from pure elemental diversity, but also from temperature diversity. So on these two,
I know we have a discussion, but how do they measure that in the planets?
There are certain assumptions taken to how one would assume that. Basically, the next slide explains parts of that. So what we have here on the bottom of the plot is different temperatures in the disk, basically, and the molar fraction of the condensates at that disk, just equilibrium assumed. So a dust grain at 1400 Kelvin would be oxygen dominated, have quite a large calcium components and quite some aluminum as well. Whereas at the colder temperatures, iron is much more prominent. In this case, for example, is taken for a C2O ratio of 0.9. And in order to create Earth, I mean, there are various different formation models for how planets are formed. But in order to kind of get the correct abundances of different elements that we see on Earth, one has to have a kind of a condensate contribution function for the planet, which, based on some models by He and Wang, is looking like somewhat like this. So we take a few of the cold ones to actually get our sulfur compound correctly, and mostly of the higher formed components.
Is this the thermochemical code on GGChem?
I mean, it's based on GGChem, yes. Well, it's calculated with GGChem, but that's the equilibrium.
And the carbon then here would be...
Mostly in this range here, in this temperature range, it's actually in the grains.
Is that the soot?
That's then carbon soot, yes.
Mm-hmm.
In higher and lower temperatures, actually in the gas again. Mm-hmm. There's also whether you have sequential condensation or just equilibrium condensation makes also a difference. We go into detail of that in the paper itself. And one of the other effects, different carbon to oxygen ratio. As an example, if we would assume a carbon to oxygen ratio of 1.25, so pretty carbon rich, the overall content of carbon is quite high in most of these grains at different temperatures. So if we would assume the same contribution function of the different grains from different temperatures to form the same or to form a similar planet, just in a different disk, this planet would be quite carbon rich, would be a carbon rich planet. Do they exist? We don't really know, but in principle, they could form in such a carbon rich disk. And if one says, okay, we just form from condensates that are just at this one temperature or in a small temperature range, one could just take a slice and some of the components there. Of course, that's the bulk planet, which doesn't necessarily tell you what's in the atmosphere. The atmosphere may be different, and especially the planet will differentiate into a planetary core and a planetary mantle. So there's another differentiation process happening, especially the iron, for example, goes mostly into the core, where it's just a tiny bit of the iron actually.
But I thought the soot boiled off at 500 or 700 Kelvin.
If you are that, what do you mean?
Well, there's a lot of carbon at, pretty high temperatures. What is that, diamond or something? Or
basically graphite stability. If you're so carbon rich, you would form that. Like the soot quite often is dark carbohydrates, but you have also just pure graphite. On Mercury, for example, is probably quite carbon rich and has some carbon.
Oh, well, we can come to it in the discussion, but if you start with some soot, how do you, if you gradually heat it up, does it become graphite? Or what if it was just soot and boiled off at 500 Kelvin? Do you really have a history, a thermic? I mean, this is all equilibrium.
This is equilibrium at that temperature, and if you are at 1000 Kelvin and you're that carbon rich in our gas phase, you form carbon condensates according to thermal stability.
Okay.
So, actually, let's assume now we formed a planet. We can form various different planets. We have now a certain elemental composition that differentiates into mantle and core, and that mantle composition is also our surface composition, and somewhat will equilibrate with the gas phase. We may start with a hydrogen-rich envelope, but at least for the small planets, for the small rocky planets, that is very most likely being completely blown away. And the atmosphere is formed as a secondary atmosphere from volcanic outgassing driven by plate tectonics. There's chemical weathering, so the atmosphere actually interacts with the rock itself to get the rocks to be what's thermally stable in contact with the gas phase. So the first thing to look at is kind of this bottom layer, the near crust atmosphere, which is actually in contact with the surface. And how do we model that? mostly what I've been using is GGChem, which is an equilibrium chemistry model. So what does it do? It minimizes the Gibbs free energy of the entirety of the system. So we take a certain set of elements, put that in, we assume a pressure and a temperature. One can vary that and model a planet with a millibar, with a bar, or 10 bars, maybe 100 bars. At some point, assuming too high pressures, ideal gas doesn't hold anymore, and then ideality isn't a good assumption anymore, so it's not really applicable anymore. For 10,000 bars or so, one needs to take other equations into account, which equilibrium chemistry just doesn't. So we restrict ourselves to moderately thick atmospheres, something like 100 bars, but nothing more than that. And what was also calculated is the condensation. Condensation, we're calculating based on the supersaturation ratio. So how much of a certain gas is in the gas phase compared to how much should there be, how much is the vapor pressure of the different gas species. And then iteratively, we condense everything out so that no molecule is supersaturated anymore. So that's just how we form our condensates. And then we basically distributed again our set of total element abundances to the gas phase and to the condensate phase. And everything is in chemical and phase equilibrium. If we do this, we can do that for various different sets of compositions. We actually, if we restrict ourselves to CH and O atmospheres, we actually do get out as a most stable set of molecules, a set of these 4 molecules of methane, nitrogen, carbon dioxide, and water, which is based on Gibbs free energy, the most stable thing. If you add some H2 to that, it would react with the carbon dioxide, probably on relatively long timescales, or if you have sparks or something, to methane and water. Oxygen would deplete the methane to form CO2 and water, and so on. And basically, based on this, you can kind of define different atmospheric types. Basically, one atmospheric type having these 4 molecules, and then another one, as soon as we add enough H2 to it, to basically completely deplete our CO2. We cannot have negative CO2 abundances, so it basically replaces the CO2. So there's a CO2, methane, N2, and water as one other atmospheric type, and also there's one, if you add more O2, that has O2, N2, CO2, and H2O. So those are basically 3 different atmospheric types, just based on stoichiometry. Does that hold true if we actually calculate it based on the Gibbs free energies, or is it just a stoichiometry thing? We checked that, and actually, it's this plot that I want to show. So on here, we see different panels. Each panel represents the abundances of one molecule. What are the axes? The axes are on the y-axis, oxygen on the top, pure hydrogen at the bottom, basically an O2H ratio, just slightly different calculated, that we don't go to infinity for H equals to 0. So just O minus H divided by O plus H, and carbon content on the right-hand side. What we see is that we actually do have the 3 different atmospheric types. Like in the top left corner here, we have the oxygen, water, CO2. Bottom left, we have our H2, water, and methane. And in the middle, in this kind of triangle shaped, we have the water, CO2, and methane, with a bit of H2 intruding into it. That is basically the temperature influence. So at the higher the temperatures, the impurer our atmosphere gets because of the delta S term, the entropy term in the Gibbs free energies. On the right-hand side, you may also see carbon monoxide that shouldn't really actually form, because there you're so rich at the cold temperatures that you will also again form some graphite. So in cold temperatures, you don't reach this point because you're super saturated in graphite. But overall, we see these three different atmospheric types, and one could summarize them in this kind of table of like tick boxes of which atmospheres you have. So ideally, it would be quite cool if we would see a rocky planet and see, okay, we detected water, methane, and H2. Okay, cool, this is a type A atmosphere, and that would constrain our planet to that atmosphere, which would be pretty nice to kind of sort those planets into those. What that would actually tell us about the surfaces is one of the next steps I want to talk about, and that's what I did with a master student of mine, at least actually in a well, more than the summer project because it took more than the summer. But we started off calculating various different surfaces. So in this plot, each of these stars don't care about the names. Each of these stars represents one run, and we have looked at the surface compositions and the gas compositions. The gas composition is dictating now where we are in our diagram here, and the surface composition is kind of the color here. There are many more condensates that are present, but in this plot, for example, we focused on just the stability of different sulfur-containing molecules, and we actually see that the CaSO4 is only present in those type B atmospheres, whereas the FES is basically throughout the type A and type C molecules, and the coexistence of those two, or actually the CaSO4 and FES2, is just somewhat on the lines, which was already quite cool. So if we could constrain our planet by detecting an atmosphere to a certain atmospheric type, like type B, for example, we could say, oh, we expect CaSO4 to be thermally stable at the surface. So by saying, cool, this one atmospheric type is there, we expect this certain mineral to be there.
This is just a trace amounts of sulfur introduced into the atmosphere, or do you have
all of these models are not run for just CHNO, but for a larger set of elements. And we ran the complete chemical equilibrium for a large set of elements, 18 different elements actually. Mm-hmm. So we also get magnesium, iron to actually model the surface as well.
But you don't have nitrogen dominated atmosphere.
Some of these are nitrogen dominated, some of them are not, depending on the set of element abundances. And here we have just a few models. So one thing that we wanted to do is to actually run the entire parameter space. Because if you can, drawing lines here, sure. I was convinced that this is of the entirety of type B, but here we haven't run any models, at least in that paper yet. So we would need to run models that are here as well. So we actually looked into the entirety of the parameter space. And once we do that, we actually didn't change all of the elemental abundances, but we kept one set of total element abundances for all elements except for H, C, and O. And so we vary H, C, and O so that we can cover the entirety of the parameter space in this plot. All of the other elements are staying the same. Earth abundances means in this case that at 300 Kelvin, this composition, the initial composition, is resulting in a Earth-like atmosphere. We change all of the abundances of CH and O so that we cover the entire parameter space, and we see that it actually very neatly coincides with the different atmospheric types. So the SO4s are just in type B, and FES is in type C and in type B. It's a bit jagged on the edge because there are occasional atmospheres that actually equates again to the coexistence of some certain molecules, but the other jags are just jagged lines are just interpolation of the data. Running that for, that's not how it's supposed to look. Usually, this entire thing should be red. There should be no blue behind it.
We'll imagine.
Imagine this to be entirely red.
This is like the left one.
Like the left one, except for this purple one. The purple one actually is correct. I don't know what's happening with the interpretation of this here. It's a PDF. It shouldn't happen. But okay. There is a region here, which is the existence of SO4 condensates and together with the FeS2, which actually equates to some sulfur dioxide being in the atmosphere as well. So that's then additionally on top, you can have the variation in sulfur abundances in the gas phase. Good. This other composition now looks good again. That's based on Ryugu compositions. So imagine the one before looking basically like this. I have no idea what happened there, but okay, I have to investigate that. So the next thing what we looked at is the average oxidization state throughout all of these models. And we see for the Earth model, well, that also coincides with the atmospheric types. And actually quite interesting to note here that even though you have the same O to H ratio, which is one value on the y-axis here, you can end up in different mean oxidization states of the rock. So just looking at O to H doesn't tell you the entire story. Also, just looking at the C to O ratio, you can get completely different results in this here if you change the O to H as well. So there are multiple things you have to take into account to properly characterize your planet. I hope you can see that online, that the type C in this case here is slightly different in color than the bottom. So there is actually an in-between state as well, which doesn't occur for all planetary compositions, but for some of them. So in the Earth case, this is all blue, this is all iron 2, but in this case, it's purple. It's actually a mixture of different states. The Ryugu one is actually quite more distinct there. So for I should say Ryugu on top, I think. But anyways, yeah, for this model here, no, sorry, that's Earth for 500 Kelvin. Sorry, Earth 500 Kelvin, we actually see that there's quite a change in the mean oxidization state for the type C, but still very distinct from the type B and type A atmospheres. If we don't want to just model the atmosphere-crust interaction, but an entirety of an atmosphere, things get more complicated because you have to assume a certain pressure-temperature profile. Ideally, one would self-consistently calculate the incoming radiation with the atmospheric composition. But at least from what I'm showing here, we're focusing on a fixed PT profile, just very simple polytropic atmospheres. And we go through the atmosphere. We solve chemical equilibrium in every atmospheric layer. And whenever something is thermally stable, we remove those molecules that are thermally stable and put them at the side, which are then our thermodynamically stable clouds. And we just remove the gas phase, or we take the gas phase to the next layer. So we actually deplete our total composition of the atmospheric layer above with respect to those elements that are condensing out. How does that change our composition? Well, spaghetti plots incoming. We have pressure on the x-axis, so the bottom of the atmosphere is on the right-hand side, and atmospheric composition on the y-axis. So the higher up, the more stuff of it is. Yes, this plot goes to basically non-existent molecules on the bottom of the y-axis, but that's just to show the effect of the cloud formation. Especially in this case, the water composition, the blue line here, goes from being the dominant species to basically not really present in the atmosphere anymore. And the atmosphere is then dominated by methane and nitrogen and some ammonia. So this is all caused by the condensation of clouds. And actually the clouds that we have are water clouds.
It's
Two different lines.
isothermal atmospheres, are they?
No. These are
Surface.
the polytropic
Oh,
atmospheres. If you have an isothermal atmosphere, you keep the same temperature but reduce the pressure. So you work against thermal stability of condensates. In an isothermal atmosphere, you don't expect any condensate to form because the vapor pressure is basically dependent on temperature, and that if you then remove or reduce the overall pressure, so also the molecular pressure, the partial pressure of each molecule, you get lower supersaturation ratios. And if we start with S equals to 1 at the bottom, we go throughout the along the isotherm, you go to S smaller than 1, so no condensation. You need to have a decreasing pressure temperature profile to form condensates. So yeah, we form the condensates, we actually take them out, and we see here, well, we have water clouds throughout the atmosphere, ammonium hydrosulfate in the upper atmosphere, and also a bit of ammonium chloride, and also graphite in the bottom of the atmosphere. Ideally, we would like to look at this plot individually for all elemental composition, all surface pressures, all surface temperatures, 1,000 plots to look at. Let's just make simpler plots, which are
5 minutes left.
5 minutes left, that's good. So we don't look at 1,000 plots, just a handful, but we kind of condense them into one diagram. So we have surface temperature now on the x-axis and the local pressure on the y-axis. The dotted lines are the temperatures at the actual point in the atmosphere. So 400 Kelvin atmosphere starts here and we go up, hit 300, 200, 150 or something at the very top. And now we basically plot contour lines now for the different cloud condensates that are present in the atmosphere. And here it comes. There are a lot of them. Depending on the composition, we get quite a lot, quite different colors. Not necessarily important right now to distinguish all of the colors, but we especially see low temperature condensate and high temperature condensates. Looking at a different composition, we get basically the same picture. And actually the only condensate that is thermally stable in between those two layers of the high temperature and the low temperature clouds is graphite, but the others basically form distinct layers.
This would be like, it would settle out. I'm trying to imagine, what is a graphite cloud? Doesn't it just all rain down to the surface? Or?
Well, as long as you assume that you have convection, you would rain out and you would bring it up again. Like on Earth, on Earth where we do have the convection, we drop down a lot of the water, but it will get evaporated again. And then there's basically throughout the, looking globally on our Earth, throughout the troposphere, we have clouds at any layer, basically. So this is kind of an expected global average of the cloud formation for those planets. If we change not just a constant surface temperature, but a constant surface pressure and changing the pressure, but rather changing pressure and temperature in a way that we always go through 1 bar at 300 Kelvin, we see, as in this case, for example, that there are water clouds for any of those surface conditions, but not all of them reaching towards the ground. So just as an interesting side note here, if you see a water cloud on a planet, doesn't necessarily immediately mean you have water on the surface. You can have a dry surface, which is either dry, but the pressure and temperature are still fine for for water that it could exist, but it's just a bit too hot to actually reach the surface, or too dry in general. Or you have a really hot surface and a high surface pressure that you just can't condense water down there. But you can have some cloud layers of water. Also, putting all the other clouds there, actually, the only one that I really want to mention is this pink one up here, which is H2S. And actually, that only forms if it's quite cold and relatively low pressures. But you also have to have the sulfur. And in order to have the sulfur, you either have volcanism that can produce a short-lived H2S, H2SO4 cloud, like acid rain on Earth. But if you want to have it over long time scales, you kind of need to have a constant reservoir of sulfur. So that means you have to have a high surface pressure and surface temperature. So basically, seeing H2S indicates to you we will have a high surface pressure. Venus, for example, H2SO4 clouds, high surface pressure, high surface temperature. So seeing that on an exoplanet would restrict or would constrain our planet. I already mentioned this, that we can have water in the gas phase for the case of no clouds, can have water in the atmosphere for just high water clouds. And like on Earth, we have water vapor in the atmosphere. Oops, spoiler. We can have water clouds throughout the atmosphere and a water puddle on the surface. But in the high parts of the atmosphere, they can look pretty similar. So that's also one of the dangers in interpreting spectra at some point. So I also mentioned this. We can have two different sets of cloud layers, basically, in the picture here, flying in Austria. Well, these are both water clouds, but imagine this as two different compositional clouds, one of them being hidden. If you fly through the atmosphere, you could see it.
Well, the atmosphere in Austria looks pretty dangerous.
Well, that was a good flying day. But it was a lot of uplift that day. But if we have H2SO4 clouds, this wouldn't be Austria anymore. This would be Venus at some point because we actually have a high surface pressure. So good that I haven't detected any of these cloud species in Austria. Otherwise, it would be even warmer there than it already is anyways. Last minute. So the only thing I want to mention is observability. We calculated for various of these different atmospheres. We calculated some theoretical mock observation spectra. This is now far too good resolution to actually be observed. But just want to highlight some of the differences of the different atmospheric types, color-coded. You can see the position in the kind of triangle diagram up here. And also just because they are quite similar in the CO2, for example, like the red one can be distinguished quite, in quotation, easily to the purple one, although the CO2 feature looks quite similar. And in principle, they are kind of distinguishable. The different atmospheric types are relatively unique, but observations with JWST or Ariel or so will be quite difficult, because if we look at the actual y-axis of the feature depth, well, if anybody who knows a bit of the error bars that we expect, yeah.
Well, we can come back to this.
We have to look at a lot of transits and quite some favorable planets. So take-home messages, I leave them up because I'm running out of time. Thank you for listening.
Great, thank you very much. So we have time for questions and a discussion. So maybe Ryan can help me in Virginia, and if the questions here who are online, just raise their hands, of course. To what extent then, I don't know, you calibrate against Venus or some more? Do you have dedicated setups for, of course, some of the solar system planets, and how well does the model work?
For For Earth, for example, we changed the element abundances so that we fit Earth composition. Earth atmospheric composition works quite nicely. Of course, we don't get any methane in the atmosphere because the methane and the oxygen together, they're just not in chemical equilibrium.
Right.
They're caused by biology.
Mhm.
So that we obviously don't have.
And the presence of the ocean you can deal with?
If I set the model up that water is present at the surface, that we are saturated with water, yeah, sure, no problem at all.
Mhm.
That is quite easily possible. For Venus, wasn't me who's doing it, but Peter did other models for Venus that fit pretty well. There are some minor disagreements, but they're basically caused by some photochemistry.
Mhm.
So the photons changing some of the atmospheric composition.
Mhm. Any questions in Virginia there or online?
Yeah, we have one, Jonathan. I have a question. Hi, Oliver. Very nice talk. I wanted to rewind to pretty close to the beginning of the talk where you showed this disk model condensation sequence.
Because that's the only one that you are not familiar with, I see. Yes.
Well, yeah, the other stuff. We did our PhDs together, so the other stuff I did quite well. So the bottom plot, you make a grid in temperature with ggchem, or this work does, right?
Yes.
I was hoping you could talk a bit more about the contribution function above it, because that seems quite crucial to the overall composition you get in the previous slide, right, for the planets' abundances. So like one feature that sticks out for me is if you could just explain what the cutoff at 1400 Kelvin is. What the rationale for that is.
What is this function? What is this contribution function?
This contribution function is basically a fit to create Earth. So one of the main points that we're actually investigating in the paper is condensation temperatures of the different molecules or different elements. So at what temperature 50% of the given elements is in the condensate phase and no longer in the gas phase, which is kind of what geologists have always been looking at in fitting the different compositions of Earth, Venus, Mars, for example, that they're slightly different in some of the abundances. And the condensation contribution here is basically a fit to create Earth. So if you change the condensate composition because you kind of do a slightly different model, then you would need another contribution function to create Earth. So it's basically a hen and egg problem of what comes first and how do you actually fit it, because it's two fitted things put together to create Earth.
That's very carbon poor. I'm trying to remember. I'm actually misremembering.
Compared to what is always the question.
Compared to solar.
It's pretty oxygen rich because you see that effect also here, where the overall contribution of the of oxygen is always pretty high.
So when C2O says 0.9, that's not what goes into the planet.
Well, that's the disk.
That's the disk.
C2O in the disk, and we see that in all of the condensate because they are basically rocks. Rocks are always or almost always incorporating oxygen to it because they have the SiO2, for example, as a major contributor. So they are always providing a lot of oxygen. So the overall oxygen budget of Earth is pretty high.
Does that answer your question there in Virginia?
Partially. So if I understand correctly now, so you have this elemental abundance in the disk, and then you ask the question, what contribution would I get from this in order to form a bulk silicate Earth composition?
Well, it would actually be a bulk Earth composition.
A bulk Earth. Okay.
Because the next step is then to have the differentiation and into core and mantle, so that most of the iron actually goes into the planetary core, and that just some of it stays in the mantle, available for the surface, for example.
Okay, so at the moment you're assuming everything is just is it right at the crust?
No, this for this part of it is actually bulk planet, and everything that I talked later about is just the element abundances that are available for interaction with the atmosphere.
So you have another model for what differentiates in the.
These two models are not linked. This was just
you are what we saw later did have a crust that was the iron had settled down maybe.
Yes, we chose compositions where basically the iron depleted. But in principle, there's nothing against a planet that is quite iron rich. Mars, for example, is relatively iron rich at the upper parts of the mantle.
Well, let's see. So does that mean the atmosphere that we see, if we could measure the thing you showed at the very end, is that going to depend a lot on how things have differentiated in the crust and world?
So the atmosphere that is to be detected is basic, or can be roughly assumed to be in contact with the upper parts of the planet. And whether or not that planet has a thick planetary core or not doesn't, in the first order, change the atmospheric composition. But it may change the tectonic regimes that planet has. It may change the overall.
What if all the iron has settled to the core and is not interacting with the atmosphere? Does that change something?
It depends on when it got to the core, because whether or not it goes to the core as pure iron or actually as iron oxides, or whether it takes the carbon with it. There are some interior models that actually say that iron carbide should settle to the core and therefore reduce the carbon content for the upper parts of the planet. There are quite some steps in between the kind of planetary formation and the atmospheric detection in the end. I included this here to basically talk about both ends. I mean, you and some others are working on planet formation, so that's why I included that to talk about both ends of the spectra, basically.
Right. There's two complicated things, at least two complicated things to worry about.
2 is very optimistic. N definitely greater than 2. And then atmospheric circulation will complicate everything, that the day side is different to the night side. We get clouds which complicate our observation. The spectra shown at the end are just cloud-free spectra. So features will be actually even smaller, so even harder to detect. But maybe with some, we are currently running quite a lot of spectra throughout the entirety of the parameter space, so that we can we try to see whether it's possible to kind of disentangle those two to the different.
Are there other questions in Virginia?
Types.
I was going to ask then, you mentioned this maximum pressure you're comfortable with.
Yes.
But if I did want to do a thicker atmosphere, what would you need to do here? I mean, and have you got GGChem models that would work okay on the Jupiter in any regime, or
Jupiter for the upper parts of Jupiter, where the pressure is low, no problem. Where pressure is low, it's never really a problem.
But unless it rains out, and then you lose it.
You lose some elements that condense, and you take them out. That's a question how you want to treat them. If you go through to very high temperature or very high pressures within Jupiter, it's not an ideal gas anymore. So the deeper you go in, the further away from reality an pure equilibrium chemistry model gets. If you take into account fugacities instead of pressures, because at some point you get some correction terms, due to the non-ideal behavior, fugacity factors that basically can change the results quite drastically. But just in our model setup, we just don't have those, so we cannot, and therefore we don't want to model those.
Well, that comes to these Hycean worlds, and James Webb is detecting some of these sulfur compounds, and
no, James Webb is not detecting any sulfur compound in K218b.
Well, so what is your take on that then?
There's ethane. If there is a bomb in the spectra, which is very debatable, but if there is a bomb, ethane, I think some of the people that are currently in Virginia have been working on that, so feel free to state something on that. Don, please.
Yeah, I mean, I'm on the paper. I didn't do really any of the modeling, but because they wanted to do it turnaround very quickly, and I can't forward model that quickly. But the upshot is exactly what you said. Basically, it's the CH bond that is generating that feature. So if you add sulfur into it, you still have, or not, you still have some feature in that region. And certainly with the signal to noise that they have, you can't discriminate it. So for me, it's a little bit, they had a hammer, which is DMS and DMDS. And so everything in the atmosphere looks like a nail to them. It's the simplest way I can put that.
And basically, if you say, oh, I want to have sulfur in the atmosphere, and if you force it to have sulfur in it, sure, it will spit out some sulfur. And the sulfur that is not having a feature in any other region is dimethyl sulfide. But the feature is not caused by the sulfur, it's caused by the CH. So, and in general, the number of data points and the number of free parameters, if they are on the same order, be very careful with what you're fitting.
All right. Any other questions for Oliver? Perhaps we can just finish these three types of atmospheres you mentioned. Can you say a little more about the significance of these three types, and do we expect? I'm trying to think how to phrase. So, an atmosphere will be in one of these three types, or can it be sort of more intermediate, or what exactly is the significance of these three types?
So, if I just go back to this plot, whether or not I have like 10% oxygen or 20% oxygen, I should be lying like somewhere on this green line, basically. So the composition here is without N2, because throughout the parameter space, basically N2 is always there. So this is the everything but N2. So Earth actually lies up here with like almost pure oxygen atmosphere with a bit of water and a bit of CO2. But basically, there are clear cutoffs between the different types. So whether I have a bit of oxygen, I still lie in this type B atmosphere. As soon as I get no oxygen anymore, I will get the methane in it. So there are quite clear-cut atmospheric types. Also within the condensates, we see quite clear cuts. One other aspect of this is the coexistence of carbon dioxide, methane, with water as well, but no carbon monoxide, is something that some people have been claiming to be a biosignature. According to this model, the equilibrium chemistry, there are quite some planets that can produce this coexistence of carbon dioxide and methane. Not a big problem at all, especially slightly higher temperatures. No problem at all. So using that as a biosignature, if equilibrium chemistry already can explain it, very problematic. Looking at on the other side of like O2 plus methane, whole other story. That's an actual disequilibrium that can do something. And we have seen at least one certain planet with the coexistence of CO2 and methane, actually K218b, actually does have the coexistence of those two molecules. DMS is just overfitting. But looking at the actual things that are there, those are actually good detections. There's a good detection of CO2. There's a good detection of methane. There's a good detection of water. Those three molecules are there. And that's basically showing that's either this type, if it's also actually quite hydrogen rich, it's again a signature of photochemistry, because actually in the type A, you can also produce some.
But can you remind me, can we tell in K218b if it's a primordial atmosphere or a secondary?
It's a mini Neptune. It's not a Haitian world, because Haitian worlds don't exist, at least in the in the term of inside the habitable zone, because they would just be two.
How do we know
that? Plots. If you look at atmospheric models of them at that distance to the host star, their surface is will get quite hot. And if you have such a hydrogen rich or H2 rich atmosphere, you don't have a water ocean anymore at those distances. Further out, maybe, but that's different planets again.
But do we know if it's a secondary atmosphere or a hydrogen dominated atmosphere?
Probably quite hydrogen dominated as well. And then I don't actually know how hydrogen dominated. If somebody just knows off the top of their head, but H2
I don't know. I don't know off the top of my head, but there's the Schlauen et al. 2024. This was a pretty comprehensive reanalysis of the data. I think that's the title, actually, comprehensive reanalysis, from the near spec observations from Medusa et al. And there they do a pretty good job of showing you can fit mini Neptune hydrogen dominated, basically what you would expect from a primordial atmosphere of that kind of planet, to the observations. So it's very much dependent on the modeling that you do, what kind of atmosphere you think. So I don't think they really have any constraints on if it's a primordial or a secondary atmosphere.
And then again, the CO2 feature is just photochemically produced, like in other hot Jupiters, where we have the actual SO2 features in an H2 rich environment, which is just photochemistry.
Okay, last question that I have is, and we should finish soon. So if I have a primordial atmosphere, so hydrogen rich, maybe quite a lot of volatiles, which interacts with the crust and then is evaporated away, can I tell later on from the secondary atmosphere that's still there that there was this prior phase or not? I know we've discussed this in the past, but any quick thoughts on that?
The quick thought is that the primordial atmosphere for most close-in planets, for the smaller ones at least, will be lost very quickly.
Well, but if it's there for some tens of millions of years, 100 million years.
100 million years, probably. Let's assume for 100 million years. It is during the magma ocean stage. It will put quite some volatiles into the melt.
Yeah.
But those volatiles are especially water and carbon dioxide, some sulfur, some nitrogen, maybe some other species. And some of them can be kept in the mantle for longer than the actual primordial atmosphere survives. So the primordial atmosphere itself will be completely gone. So there's no connection to that directly anymore. But there's the next step of how you dissolve some of them into the melt. The melt keeps it in the mantle. You form a crust probably on top, and then you're volcanically outgassing from it. So the initial stage of the planet dictates the overall volatility constants. But how unique that is,
we've got to run some models.
Yeah. And how much you can actually differentiate the CO2 and the water, and the water to CO2 ratio. I'm not an expert on on actually the dissolution in the melt, so that's going to be quite difficult to model, but possible in principle.
Okay, then I think we should finish now. So let's thank Oliver again for a great talk and discussion.